get comfy, keep enjoying your coffee, and we will crush this AP Physics C problem. So this is an AP Physics C problem from 1998. It's the first question from that year. And what we're looking at for this electrostatics question is we have a small sphere in this diagram, point A right here. It's super tiny, but there it is. And it has a charge of 120 microcoulombs. The larger sphere B has a thin shell of non-conducting material, so that means the electrons won't move on its surface, or the charges, or whatever they are. They're kind of held there. And it has a net charge that's uniformly distributed over the surface. The sphere has a mass, okay, this is neat. They gave us a mass of 0.025 kilograms. We've got a radius on it, and it's suspended from an uncharged, unconducting thread. So it's just like floating there, well, being held there by tension. And it's in equilibrium with the thread that makes an angle of 20 degrees with the vertical. The centers of the sphere at the same vertical height and the horizontal distance of 1.5 meters apart is shown. Okay, this is cool. This is a neat problem. In part A, we're asked to calculate the charge on sphere B, and basically all we know is that we have a charge on A, 120 microcoulombs, but B is just like suspended there. Now, if we actually look at the forces acting on B, we get a really good idea of what's going on. We know the forces acting on B are a tension acting up here. Because B has some mass, there's a weight or a force of gravity. I like to write weight, which is your mass times gravity here. And then we also know, and this is the big one, that charge A in the sphere B, which is charged because it's being pushed away, it's being pushed away by a repulsive force. And this is some force due to the electrostatics. Okay. Now, if it's being held in equilibrium, what we can say here is that the sum of the torques acting on this sucker have to equal 0. And they have to equal 0 in every direction for it to just be at rest. It's not accelerating or rotating in any direction here. Now, I don't care about the vertical forces. If we were to break up this tension, I could break up this tension into a vertical amount, if I would draw a little better, a vertical tension, and I could also break it into a horizontal tension, like this. I don't care about the vertical tension because I know that this vertical tension right here, that's just going to be equal to the weight, because our vertical forces up and down have to cancel out. They have to be equal and opposite. Otherwise, this little ball here is going to go up or down. What is super helpful, though, is that this tension acting in the x direction to the left is going to equal this electric force pushing it to the right. All I need to do is figure out what directional component of the tension is that in the x direction to find it. What's super nice here, if I kind of draw a little picture off to the side, this is the line where this is theta, and we know that tension lies along it like this. If I kind of make a box around this, it's pretty easily seen that this right here is theta as well. So what I can do here is I can say, look, I want the tangent, or I want the tension component that is going to that left direction. Which, if I take a look at this triangle, this is the opposite side of the angle, and this tension is the hypotenuse. So this must be the sine component of the tension. So what I can say here is that, and we'll assume that acting to the right is positive and the left is negative. What I can say here is that the electric force acting to the right minus the force acting to the left, which is this tension sine of theta, that has to equal 0. which means that the electric force equals the tension sine of theta. And if we remember anything about our electric forces, we know that due to Coulomb's law, this electric force can actually be written as K QQ, so Q1 and Q2 over R squared, where that R is the separation distance of our two charges. And this has to equal T sine of theta. I know what Q1 is. That's the charge on A. Q2 is the charge of B, and this is what we're looking for. So now I just got to go and solve this problem out to get what we want, which is pretty straightforward for us. It's kind of nice. To do this, let's just say QB equals, I'll multiply by R squared, divide by K and QA. So I'm going to get T sine 20 times R squared over K QA. And I guess the one thing that we need to do in order to get this tension is to recognize that in the vertical direction, this cosine component, we need to be able to say that in the vertical direction that the T cosine of 20 has to equal mg. So this is our x direction here, but this is our y direction. So what we're able to say here is that our tension is equal to mg over the cosine of the angle, which is 20. Now I can substitute some stuff back in. I can take this mg over cosine 20 and plug it in for t, which will yield me here with mg sine of 20 r squared over k qa cosine of 20. If I wanted to, I could recognize that sine over cosine is a cotangent, or is a tangent there, and just run that. So that'd be like tangent of 20. But at this point, I just shove in all the numbers I have. M is the 0.025, G is the 9.8, sine 20 is a value, the R is 1.5, make sure you square it, divide by K, which is our 9.0 times 10 to the 9th, and QA is 120 times 10 to the minus 6th, and then cosine of 20 is some quantity. We just push those numbers all the way through on a calculator, and we will find QB, which equals we'll round up, 9 times 10 to the 7th, negative 7th coulombs. Okay? So that's that. It's kind of more of a forces problem for mechanics than a real E&M problem, but we're using our mechanics ideas to solve for E&M things. Okay? In part B, we are going to replace sphere B with a slightly different sphere. It has the same mass, same radius, same amount of charge, but this time it is a conducting sphere. Once again, we kind of drifted off so that an equilibrium position is stabilized, but we're being asked, is the equilibrium angle less than, equal to, or greater than 20 degrees? So what we're being asked is if this is A out here, and then this is B2, is this angle greater than, less than, or equal to 20 degrees? Well, what we're actually going to be able to see is that if we magically just transform B1 into B2, a non-conducting into a conducting sphere, what we would find is that on a conducting surface, all of the positive charges that would be scattered around, the positive charges want to get away from the positive charge A here. So what's going to occur is that these positive charges, they're actually going to drift away to the back side of the ball. And not completely, but they're going to move away a little bit. When they move away, this ball is going to become polarized with a net negative charge on the left and more of a net positive charge on the right. Now this positive charge is still a larger amount. The positive and the negatives, when they add up, you get back the 1.9 times 10 to the minus 7, which is positive. But because these charges have moved a little bit further away by like the radius of the ball, these two objects are no longer 1.5 meters apart. They are 1.5 plus the radius of B2 away. So that radius distance is that extra bit they're further now. Because of this, when we look at that electric force, which is that KQQ over R squared, we have just increased R squared, which has reduced the electric force, which means that this ball wants to fall back to the left a little bit so that it can decrease this amount back to the 1.5. But in doing so, we're at a much shallower angle. So our angle is actually going to decrease. It's going to be less than the 20 degrees before in order to make up for that missing electric force there, because those charges have moved away to the other side. So that's what's going to happen there, and that's the justification to it. What we now have is we start getting to the calculus section of this test, or this problem. And we've got sphere B being replaced by a very long, so an infinitely long, horizontal non-conducting tube. Is shown in the top view below. And this top view isn't really great, but it's just a very long, hollow tube. It's hollow with thin walls of radius r, 0.2, and a uniform positive charge per unit length of lambda equals positive 0.1 microcoulombs per meter. We are asked to use Gauss's law to show that the electric field at a perpendicular distance r from the tube is given by the expression E equals 1.8 times 10 to the third over r, where we're outside of the tube and r is in meters. It's actually kind of nice that we're outside the tube, because if we were inside the tube, the electric field would immediately be zero, because we're containing no charge inside of that. If we kind of draw a picture of this thin, non-conducting tube, what we're going to do with Gauss's law is we're going to draw a Gaussian surface on the outside of this tube here, and our surface shape is going to be like a nice circle we've got there. And when we do this, what we can say here is that for Gauss's law, a closed integral of the electric field passing through some surface area is equal to the charge enclosed inside that loop over epsilon naught. Now, what we are going to choose for our surface area here is we are going to choose like a soup label of a cylinder. So if we kind of draw this 3D, like this, the electric field is going to be coming out perpendicular to the surface of this blue hollow tube. And that means it's going to be coming through an edge of our soup label like that. With our edge of the soup label like that, what we can say here is that we just want our area to be not only the loop going around the 2 pi r, but how long it extends for. So by an L value there, okay? So what we're going to have here is, because this electric field is constant all the way around that circle, it is decreasing or changing as we go away, but on the circle itself or on that soup label itself, it's constant. We can pull this electric field to the outside, which just means that we're taking a closed surface integral of area pieces. When we take that integral, we just get back the area we want. So what we're able to say here without really doing any calculus, just by kind of making an argument, is that the electric field times 2 pi RL, really that's just the area, equals the charge enclosed over epsilon naught. At this point, we have to be aware of what is our charge enclosed, and this is where things get tricky. Well, our charge enclosed is really dependent on how long is our tube, or what section of the tube are we looking at, because our tube is very long, it's near infinite. Well, we are given here a linear charge density, which is essentially saying that the charge is equal to some charge density times a distance, a length along the tube. So we can say this is equal to lambda L over epsilon naught. By doing this, we're actually able to wipe some stuff off of our problem. The lengths don't actually matter. They completely go away. And all we see here is if we divide by 2 pi r on each side, we quickly find that our electric field is equal to a number of constants, lambda over 2 pi epsilon naught times 1 over r. These constants here, when we run them all together, they will give us the 1.8 times 10 to the 3, which is what we're trying to prove. And that's how we do it with Gauss's law. Okay? So that's all that's going on there. Nothing too crazy. In part D, we have a small sphere with charge A. Hey, it's the small A sphere again. 120 microcoulombs is now brought into the vicinity of the tube and held at a distance of r of 1.5 meters from the center of the tube. Calculate the repulsive force that the tube exerts on the sphere. So in this case, all we need to do is we're looking for a force. We know a force is equal to a charge multiplied by an electric field. We know the electric field at this position because the electric field is just 1.8 times 10 to the third over r. So all we need to do is say, hey, look, our charged particle, which we're bringing in, 120 microcoulombs, so 120 times 10 to the minus 6th coulombs, multiplied by the electric field, which is 1.8 times 10 to the 3 over 1.5, will give us the force applied there. And remember, electric fields are in newtons per coulomb, so we do get newtons back at the end here. I should put this up here, newtons per coulomb. And just crunching those numbers, we get a value of something around like point something. Oh, what is this? 1.8 times 10 to the 3 divided by 1.5 times 120 times 10 to the minus 6th. 0.144. I'll just say 1.14. Let's just do that. Nice and easy. So that's not bad at all. Last but not least, we're asked to calculate the work done against the electrostatic repulsion to move sphere A towards the tube from a distance of r equals 1.5 to a distance of r equals 0.3. So we have this tube. We know the electric field is, acting outward equally in all directions. We are taking a positive charge and moving it from one position to another. So we are doing work against the electric field, or the electric field is doing negative work, if you'd like to think about it that way. But we are thinking about work here. And what we can do here is we can say that work is equal to, and there's two ways to do this, really dependent on up to you. You can say work equals Q delta V, which will really give Q times the integral of your voltage here. So you'll need some voltage set up there. What I'm going to do, since we are given distances in this problem, R and R, I'm going to set this up so that work is going to equal the integral of a force through some path. And this path is going to be the 1.5 to 0.3 that we have. So our initial position is 1.5, our final position is 0.3. Now, and really this ds can be thought of as a dr because we're moving radially inwards, so we can do that, it's fine. When we do this, we need to think about the force acting on this particle. And the force is going to change because when we look at what we had up in part D, a force is equal to a charge times an electric field. This electric field is going to change because that radial distance is changing. So what we need to be able to do here is say that work is equal to, this is the integral of this force, which is Q times 1.8 times 10 to the third over R dr, because we're moving radially inward. Now this Q here, that is our 120 microcoulombs. It's a constant. It can be pulled to the outside. The 1.8 times 10 to the 3 is a constant. It can be pulled to the outside, which means this integral is getting much easier. We're going to have the 1.8 times 10 to the 3. We've got our Q for the outside, and the integral from 1.5 to 0.3 of just dr over r. Hopefully you're familiar with this integral, dr over r. This is a common integral that you'll see in the world of physics. It pops up in calc because you got to learn your integrals there. But this has the form of a natural log. So what we quickly get out of this is our constants, and then our integral will be the natural log of, and then remember it's our top bound minus our lower. So 0.3 minus the natural log of 1.5. If we remember our log rules, we remember that when we subtract two logs, we can actually divide by the quantities of them. So we're going to get here, and I'll pull my constant down again, 1.8 times 10 to the 3, and then our Q is 120 times 10 to the minus 6 coulombs, times the natural log of 0.3 over 1.5. Boom. And at that point, it is just a matter of crunching the numbers and seeing what we get. Let's see if I do this real fast. It's a natural log of 0.3 divided by 1.5, boink, times 1.8 times 10 to the third, times the quantity of 120 times 10 to the minus sixth, and I get 0.347 or 0.35, and that's units of work, so those are joules. Now, if you threw this on your calculator, you might have found that this popped up as a negative number. For one, I don't care about that negative at the moment, because what they are asking us to do is to find the work done against the electric field. The work we've actually just found is, we can think of it as the work the electric field is doing. And since we are moving it against the electric field, that work is technically a negative quantity whenever the electric field is doing negative work. If the electric field is doing negative work, we can think about it just being work done against the electric field. So that's the quantity right there. Okay? And that's it. That's the whole problem. That's everything in a nutshell. So a little bit of old school forces for mechanics, and then all of a sudden doing some polarization of conductors, and then going into Gauss's law and work. So this is actually a pretty tough problem. There's a lot to digest there, a lot of different concepts that we needed. But in the end, we were able to solve it. Pretty tough one, though. But luckily for us, it is finished. Take it easy. Go check out some other videos and go prep for that test. Adios.